Okay, we will start this afternoon, and the topic is on the Rayleigh flow theory for combustor analysis. We literally will be using the tables that has been given into your one, which you can take it later on, and the exercise problems. We'll try and work out some problem possible, and ideally it will be good to have the calculators, but you can manage with what you have today. Yes. Okay. So we just touched upon the ramjet engine. So if you look at the configuration of the ramjet engine, so this is basically the configuration of this ramjet engine. In a ramjet engine, so you have this is the inlet part, this is the combustor part, this is the nozzle part. So in inlets, because it is flying above 1, probably in the range of Mach m equal to 3 to 5 is the range, we will be covering about the shock waves. We'll be having oblique shock waves at a number of shock waves, shock interactions, and there will be a normal shock. So the inlet is of convergent divergent geometry. We are not going to look at inlets here, but what we are going to look at here is if this is at 0, this is 1, this is 2, this is 3, then we can see here the charge that enters into the combustor at 1, M1 will be less than 1 in a ramjet engine. So combustion takes place under subsonic conditions here. So the pressure will be P1, the temperature will be T1, density is ρ1, and enthalpy H1, and the total temperature TT1, and then the total pressure PT1. These are the properties that enter into the combustor. Now in the combustor, what actually will happen is we are injecting fuel. The fuel will be injected. The fuel will mix with the oncoming air. So there will be mixing taking place in the combustor. So mixing leads to the formation of fuel-air ratio. Fuel-air ratio is the ratio of the mass of fuel to mass flow rate of air into the combustor. So it's one of the important mixing parameters. So there are a lot of details happening here of the jet mixing process and cross flows. We are not going into those aspects at the moment here. Now the effect of addition of fuel will cause the properties of the fluid to change. Now the Mach number at entering the combustor will not be the same as the Mach number leaving, but still the Mach number exiting the combustor will be subsonic. It will change, but it will be subsonic. So the pressure will be different, will change. The temperature will also change. The density will also change. And the total temperature will change. And the total pressure will change. All these properties will change. And thereafter, the flow will accelerate and then leave at m greater than 1. This is what is happening in a ramjet engine. Now today we are going to understand the way how we could determine the parameters that are leaving the combustor. So it is the density, pressure, temperature, and so on. Now if you can look at the scramjet engine, the configuration is something very generic at the moment here. So here again, you see this is the inlet part of it. Again, there will be shock waves here, but this is 0, this is 1, this is the combustor, this is the nozzle. Now the same process happens here. The flow is being decelerated. So here m may be greater than 5, and at m1 is greater than 1. That's a difference here. We are not decelerating the flow to subsonic Mach number, but we are still having a supersonic Mach number. So the pressure will be P1, the temperature T1, density ρ1, and the total temperature TT1, and the total pressure PT1, and so on. The addition of fuel, again, now it's more complex here. When you injecting the flow, you end up in formation. A lot of complex shock waves also happening here in the combustor, because the entire combustion is taking place under supersonic conditions here. Again, the main parameter is mixing of the fuel and air, because the challenge here is that the residence time of the charge is going to be reduced. Okay, so that's the reason why all the shock waves are there, to increase the whole combustion process in a very effective way. Mixing and then the fuel air ratio, these are the important parameters. Now after the combustion, the properties will change. M1 entering will not be the same as M2, but M2 will be different, but M2 will be supersonic, leaving the combustor. And the pressure will be P2, the temperature will be T2, density will be ρ2, and the pressure, total pressure is PT2, and the total temperature is TT2. Since the flow is supersonic here, we have a diverging nozzle, which causes the flow to accelerate and to leave the nozzle and to produce the thrust. Some of the common things I just wanted to pick up at this particular point here. Now, whether you're looking at a ramjet or scramjet, some of the common assumptions which you're going to do, number one is the flow could be treated as one-dimensional flow. The flow is in one direction. The reality is that, number two, there can be some small area changes, but we are assuming that the area changes are negligible. The third assumption what you're going to make here is that effects of friction are negligible. That is what we are going to consider. Under these assumptions, we are going to propose a theory so that we could understand how the properties, the exit properties T2, P2, ρ2, TT2, and PT2 are going to change. Or in other words, what is the difference, what is the ratio of these properties? So these are the things which we are interested in calculating. So to calculate this, we need to have some form of a theory. To arrive at this theory, we have to make some basic assumptions for a model to calculate this. The assumptions are the flow is one-dimensional and the area change is negligible, which means we are saying that the duct is having a constant area. That is what we are saying here, constant area. The effect of frictional forces, frictional effects are negligible. And then we are also assuming that the flow in the combustor is a steady state flow. Then the key assumption, what we are trying to do here is that we are assuming that there should be some driving force that should cause the flow, and that assumption is heat addition. Heat addition is the only driving mechanism for this flow to take place in the combustor. So we have made some assumptions here. Based on this assumption, we are going to construct a model. Okay, so the flow is one-dimensional, the area change is negligible, and accordingly we can say that this is going to be the combustor. It's a constant area. So here is the inlet 1, here is the outlet 2. Now the properties, to study this problem, we are going to consider a small section here. Small section. And to that small section, we are providing heat. This is the heat that is going to cause the flow to go in this direction. Now, all that we know that the effect of heat addition will cause the properties to change from P1 to P2. The effect of heat addition will cause the temperature change from T1 to T2, density to ρ1 to ρ2, and the total temperature TT1 to TT2, and the total pressure is PT1 to PT2, and so on. And this is entropy S1. The entropy will increase. So to solve this problem, we need to construct the basic governing equations. The governing equations are, we're going to start with the continuity equation. Continuity equation. Because continuity is based on the mass flow rate. Mass flow rate is rho A V. That's the continuity equation. Because the area A1 is equal to A2, we can write here rho 1 V1 is equal to rho 2 V2. The second governing equation, what you're going to consider, is the momentum equation. The momentum equation is P1 is the pressure at this point plus rho 1 V1 square is equal to P2 plus rho 2 V2 square. Then the third governing equation is the energy equation. The energy equation is the enthalpy. So here is the enthalpy H1. Here is the velocity V1, the enthalpy H2, velocity is V2. All the properties are going to change. So before heat addition, here H1 plus half V1 square, that is the energy equation, plus dQ is the heat that is added. That will be equal to H2 plus half V2 square. That is the energy equation here. There is no work interaction, so work is not coming into the energy equation here. Then the fourth governing aspect is the second law of thermodynamics must be satisfied, which means entropy due to heat addition will increase. S2 will be greater than. So what we are going to do, we are going to start looking at this model, start with a continuity, and then apply that what we have deduced from the continuity to the momentum. That's what we're going to do now. So let me start with the continuity equation. Continuity equation. Mass flow rate is equal to rho A V, and this mass flow rate per unit area is the mass flux, and I am denoting it with the term G, mass flux G. So mass flux G is equal to rho V, and from this I can write here the velocity vector is equal to mass flux by rho, or in other words, mass by volume is density and volume per unit mass is specific volume, or rho is equal to 1 by specific volume. Okay, so I can write here, this is mass flux times specific volume. 1 by rho is. Now I'm going to substitute what we have here. So this is 1, this is 2, this is 3, and then this is 4. So now I can write here, this is 5. Substituting 5 in the momentum equation. 5 in 2, we'll get P1 plus rho 1. In place of V1 square, I can write here G square, specific volume square, is equal to P2 plus rho 2 G square, specific volume square. So just substituting velocity as G into V in the momentum equation here. So can I now rearrange this equation, or I can just say that I can simplify this? Can I not cancel one of the rho with one of the specific volumes? Yeah, so I can do that here. So I will have P1 plus G square V1 is equal to P2 plus G square V2. G, the mass flow rate is constant, so there is no G1, G2, they are equal, this mass flux. So I can write here P2, take this P1 to the other side, P2 minus P1, okay? So I already have G square V1 on one side. Bring this one to the other side, it will be minus G square V2. Okay, or in other words, I can write here G square into specific volume V2 is equal to P2 minus P1, or I can write here P2 minus P1 is equal to, or I can write it like this, minus G square into V2 minus V1 is equal to P2 minus P1. All of you understood this, what I'm trying to do? So we end up in an expression like this, P2 minus P1 by V2 minus V1 is equal to minus G square. This is clear. So this is what we call as the Rayleigh equation. So what it means here is that for a flow with this pressure and specific volume, the mass flux here is because of minus, so this is minus G square. This is the slope, negative slope here, G square. And this is the Rayleigh line. This is the Rayleigh line. Now to understand this further, this theory, to extend it, we're going to look at some of the stuff what we know from the thermodynamics. So we can say that on a PV chart, on a P specific volume chart, this is the slope of, this is how the enthalpy line will be, and this is how the very similar but very small change here with this the entropy will be. Okay, so this is from the PVT relationships we can deduce this. Now here we are going to look at the effect of heating. What is the effect of heating on to this happening to this H line and S line. So let's start here. P, B, this is H. Now adding heat will cause the enthalpy to increase. So if this is the line H1, the enthalpy will be increasing to H2. Addition of heat will cause the enthalpy to increase to H3. So this is how it goes. So where we can write here H4 is greater than H3 greater than H2 greater than H1. Now similarly, we could also say that the addition of heat to the entropy, we can say when you add heat, you end up in increasing the entropy. So here it is S1 in the direction of heating dq. So S2, here S3 and S4. Now what we could summarize from this is, we can say that the addition of heat will cause the enthalpy to increase. The addition of heat will also cause entropy to increase. Now with this understanding, we are going to superimpose the Rayleigh line onto the H line as well as the S line. Okay, so if we try to do that, let me V. Now this is the R line. So addition of heat, so here it is, this is H1 in the direction of heating Q will cause the enthalpy to increase H2. Addition of heat will cause the enthalpy to increase. So if I continue to heat H4, and finally I'll come to a point where the H line, the R line becomes a tangent to H. So this is the H max. This is basically a thermal choking effect, addition of heat. So this is what you see here, and H line becomes a tangent, R line becomes a tangent to H, that is the H max. Now the similar effect will also be observed for an S line. So if I superimpose the R line and I'm going to heat dq, so here you see this one here. So here it is S1, entropy, addition of heating will cause the entropy to increase. Addition of heating will cause the entropy to increase from S2 to S3, and then it can increase. So then it becomes XS max. So R line will become a tangent to S. Now what is it we are going to learn from this? And then we are going to make use of this knowledge for the understanding of the calculation of parameters in the combustor. So here you can see this is the addition of heat. This is in the direction of heat, dq. When we add heat, we have not only the enthalpy is increasing, but here you can see from here to here, what do you see here? This is the effect of heating. The effect of heating will cause the static pressure to decrease. Is it clear? So pressure goes from here to here, because it goes from H1 to H2. This is the drop in the pressure. So you can see that the pressure is decreasing from here to here. Further addition of heat will cause the pressure to decrease further. Now the same effect you also see here. The addition of heat will cause enthalpy to increase, the entropy to increase, and the static pressure to decrease. Now we have to make use of this knowledge, and then we'll try and plot these effects on an enthalpy entropy diagram of a combustor. Okay, so here is the enthalpy entropy diagram. So here is the lines of isobar. So isobar is the constant pressure line. So basically we are trying to draw the lines of different pressures. So I'm now going in the direction of decreasing pressure and decreasing pressure. Okay, so here this is the low pressure, this is the high pressure. This is the low pressure, this is the high pressure. Now I'm going to choose somewhere here. This is the point in a combustor. This is the point 1. This is the point 1. So the charge is entering into the combustor at M1 at a pressure P1 at a temperature T1, a density ρ1, HT1, PT1, TT1, and V1 and S1. These are the conditions at which the charge enters into the combustor. Now we are providing the heat, and that heat will cause the flow properties to change. Now what can we say here? From what we have learned, the addition of heat, what did we learn? The addition of heat will cause the enthalpy to increase, and the addition of heat will cause the entropy to increase, will cause the static pressures to decrease. Now together with this, I'm also going to look at the energy equation. The energy equation is H1 plus half V1 square plus dq is equal to H2 plus half V2 square, which means this is total enthalpy HT1. This is total enthalpy HT2. Now what I'm going to do is I'm going to keep the enthalpy term separate and kinetic energy term separate. So I can write here dq is equal to delta H, okay, plus delta KE. This is clear for all of you. So literally what we are saying here is that we are talking about a flow. The addition of heat, when I increase the heat, it will cause the enthalpy to increase, and the kinetic energy of the flow also will increase. Addition of heat will cause both effects here, what you see here. Now, let's start at this point here, 1. What should be the next point due to the addition of heat? Due to the addition of heat, my next point should be above this, and it should be on to the right of this point, okay, but then my pressure should decrease. So my next point will be somewhere here. Understood? So that is what we see here. The addition of heat will cause the enthalpy to increase, static pressure to decrease, entropy to increase. So if I continue to heat it, this is what I will see. The other couple of things what we have to bear in mind is the addition of heat. When the pressure is decreasing, which is also means this addition of heat will cause the Mach number to increase, because here is the flow is expanding because the pressure is decreasing. The flow is expanding. Again, you see this is continuing to increase. So in this direction, the addition of heat will cause the flow to decelerate. Sorry, the flow to accelerate. Flow is going through decrease in pressure, the flow is accelerating here. And then this continues until it reaches a maximum. So which means, what do we understand from here? Now, adding heat will cause enthalpy to increase and the kinetic energy of the flow to also increase, because the pressure is decreasing, the flow is accelerating here. Now once it has reached a point, there is a unique point here. Where is it? This is the point here. This is the H max point. So we have reached this point here as H max. So at the point of H max, from the theory, it says Mach number is square root of 1 by gamma. So that is the Mach number is. So we end up in a situation where dq is equal to dH is not going to change because it has reached the maximum, plus delta kinetic energy. So once you have reached this point here, maximum, what happens is addition of heat will cause, this will not change, which has reached the maximum, will cause the kinetic energy of the flow to increase at the same rate at which heat is added. Is that clear? Because it has reached the maximum, any further addition of heat will not cause the enthalpy to increase, but it will cause the flow to increase at the same rate at which heat addition is going to take place. Now, for example, if we want the flow to accelerate, delta KE to increase at a rate greater than the heat addition, then it needs some energy, because now it is perfectly balanced. If this has to go beyond this one, it needs some energy. So where does it get the energy? It gets the energy from the flow itself. So the flow gives off its energy. So the flow gives its energy. Now the flow is able to accelerate because of the decrease in pressure here. The flow is giving its energy, so you can see the H maximum is now, enthalpy is now decreasing. The flow has given off some energy. The flow is now continuing to accelerate. So if the kinetic energy of the flow has to increase at a rate greater than the heat addition, then it has to take the energy from the flow. So the energy from the flow decreases and the flow continues to accelerate. Flow continues to accelerate because it's going in the direction of decreasing pressure, and it accelerates and reaches M equal to 1. Critical condition. So now we can see that effect of heat addition will cause a subsonic flow, because it is to be subsonic flow because it is accelerating and reaching M equal to 1. So here it is M less than 1. Addition of heat will cause a subsonic flow to accelerate to reach H max and then continue to accelerate until it reaches a critical point, M equal to 1. Now at this point, now here you can see this is S max, because that is what we have seen. We have seen that on the Rayleigh line, there are two well-defined points. One is H max, the other one is S max. So now we can see that there are two well-defined points. One is H max, other one is S max. So you reach the point of maximum entropy, so we can't go to the right any further. And I can't come in this direction because it is a violation of the second law of thermodynamics. So the way forward for me is, so this is not possible. So I need to start somewhere from here and go in the direction of increasing pressure. So here you can see this is the upper branch. What we see is the expanding flow. Now here I'm going in the direction of increasing pressure, and this is what we see here. So this is the compressing flow. Yeah, flow compression flow. Now here it has to be M greater than 1. The effect of heat addition will cause a supersonic flow to decelerate until it reaches M equal to 1. Is that clear? So what you see here, this line, what you see here is called the Rayleigh line, which is the same line as what we see here. This is a Rayleigh line here. Is that clear for all of you? So now we are going to make use of this concept to understand what is happening in the ramjet as well as in the scramjet engine. So here is the combustor process. So this is 1 and this is 2. Now I can, if I'm trying to draw the Rayleigh line, the Rayleigh line will look something like this. The theory will go to H max and then to S max. This is the upper branch of the Rayleigh line. So here what you can see here, this is M1, which is subsonic. So when you have subsonic flow entering into the combustor with the pressure P1 and the temperature T1 and ρ1, HT1, all the properties, the addition of heat will cause the Mach number of the flow to increase according to the theory. And then this, if we could analyze the upper branch of the Rayleigh theory, then we can study the combustion problem here. So which means this is at 1, this is 2. So from the Rayleigh theory, we will be able to find out what will be the pressure P2, T2, ρ2, HT2, V2, and TT2, PT2. But the theory itself is going beyond, but we are just using the theory to calculate the properties that are changing in the combustor. Okay, understood? So here, this is the flow is accelerating. Flow is accelerating. Flow is in the expanding flow, flow is accelerating. Now if we look at the lower branch of the Rayleigh line, this is how it looks like. So if we look at this as the scramjet engine, so this is the 0, 1, this is the combustor part of it, 2, and this is 3, nozzle part of it. So here M is greater than 1. The lower branch of the Rayleigh line is supersonic. The addition of heat will cause the supersonic flow to decelerate. Eventually in the theory it will go and then it will reach M equal to 1, which is the critical condition. That is the theory. So now we can see that with one Rayleigh theory, we should be able to solve the combustion main parameters. Say for example, to find out what is M2 here, what is the P2 here, what is T2 here, what is ρ2 and TT2, what is PT2, and all other parameters we can calculate from this Rayleigh theory. Okay, so that is what we'll be looking at with this. Okay, so we can see that from the Rayleigh theory, we can calculate. We should be able to calculate using the upper branch for ramjet problems and the lower branch for scramjet problems. But the theory is same, one theory. Okay, and using this, we can calculate what are the properties that are changing during combustion process, and similarly we can also calculate how the properties are changing during the combustion process. Now how does it happen? So this is what it is here. So if this is the typical situation what we have here, this is dq. Now if we write this equation, governing equation, ρ1 v1 equal to ρ2 v2. Now let me start with a momentum equation here. P1 plus rho 1 v1 square is equal to p2 plus rho 2 v2 square. This is just to show how we could calculate the properties vary across the combustor. Now, in this momentum equation, if I can take this P1 outside, I can write here 1 plus rho 1 by P1 V1 square is equal to, if in this side, if I take P2 outside, I can write 1 plus rho 2 by P2 V2 square. What I can write here. Okay, so from the ideal gas equation, P is equal to rho RT. R is the characteristic gas constant. So I can write here rho by P is equal to 1 by RT. Okay, from the ideal gas equation. And also, we know what is the speed of sound. The local speed of sound, C is equal to square root of gamma RT. So, C square is equal to gamma RT. So, we know this one. Now, we're going to apply this here. So, when we apply it, you can write here P1 into 1 plus, in place of rho 1 by P1, I can write here V1 square by R T1. Is this okay? That is equal to P2 into 1 plus, in place of rho 2 by P2, I can write it as 1 by R T2. So to this equation, if I can write here P1 1 plus, if I multiply gamma both in the numerator and denominator, V1 square by R T1 is equal to P2 1 plus gamma, multiplying denominator by the numerator and denominator by gamma, V2 square by R T2. Then I can write here this as P1 into 1 plus, can I write here gamma? What is gamma RT1? C square. Numerator is V square. What is Mach number? Mach number is V by C. So V by, so V square by C square is equal to gamma RT. So can I write here M1 square? That is equal to P2 into 1 plus gamma M2 square. So now you can see that when you have a combustor going from 1 to 2, I can write here the ratio P2 by P1 according to the Rayleigh theory is 1 plus gamma M1 square divided by 1 plus gamma M2 square. Okay, so now we know the value for P2 by P1. Similarly, we can find for, we don't have to do it for all the things, I just wanted to show how this is done. Similarly, we can also write for all other properties. Let's see whether we can try and do it for so let's say P1 by RT1 for rho 1, and V1 is square root of gamma R T1 M1. Mach number is V by C, V equal to M into C. Okay, so this is equal to P2 by RT2, here M2 square root of gamma R T2. So this gamma R will go off, gamma R will go off, R and R will go off. So what is left out? P1 by T1 into M1 into square root of T1 is equal to P2 by T2 into M2 by square root of T2. So this will go off, this will go off, and then, understood? All of you understood? So you can cancel off like that. So now we can write here T2 by T1 square root is equal to P2 by P1 M2 by M1, or other words, we can write here T2 by T1 is equal to P2 by P1 M2 by M1 the whole square. Just simple substitution there. So we can write here T2 by T1 is equal to 1 plus gamma M1 square by 1 plus gamma M2 square whole square into M2 by M1 the whole square. So now we can see in a combustor, so how this temperature change is taking place. If this is T1 and this is T2, and this ratio T2 by T1 is given by this expression. This is from this one. Now we are going to apply the Rayleigh theory. Okay, now to this equation, we can keep on deriving things, but that's not the main thing. But we need to understand the basic principles and then proceed. So let's look at the upper branch of the Rayleigh curve. Okay, so upper branch, the Rayleigh theory starts from 1. For us, we may limit it here, somewhere here, but the theory itself goes to 2, and 2 is eventually a critical point. So similarly, the same thing is valid here in the lower branch of the Rayleigh curve, which is corresponding to scramjet combustion. It goes from starting point 1. This is totally a different problem situation. So it starts from 1 and going to 2, and this is a critical point. Is that clear for all of you? So let's try and apply this condition here. Now P2 is critical point here. So I can write here P star in general terms. P star by P is equal to 1 plus gamma M square divided by 1 plus gamma. What should I write for M2? 1. Understood, all of you. Because this is critical, M equal to 1. So this is same whether it is the upper branch or the lower branch. So similarly, we can write here T star by T is equal to 1 plus gamma M square by 1 plus gamma into 1 by M square. Is that clear? So if you have, now you can take the tables in your, if you have, you should have these tables in your this one. Take these tables if you look at the second page of it, here I have given some equations here. So we have tried to reduce this equation, the first two equations, but you don't need to know or remember these equations because all of them are summarized in this table. So we will be using this table Rayleigh flow table to study the combustion properties. So now you know how to use the Rayleigh tables now. You don't need to, we'll be using these equations. This is the Rayleigh theory. The Rayleigh theory itself goes from here to here. But for us, the combustion will take somewhere here to here. Or for us, it can take from here to here. So that is what we're going to look at it. Now, how do we do it? So we have to, let's say this is 1 and 2. So let me draw it again here. So this is 1 to 2, but the theory itself goes like that. So here it is 1 to 2. So the way forward is T2 by T1, you write it in cyclic form, T2 by T star into T star by T1. Now T2 by T star corresponds to Mach 2, T1 by T star by T1 corresponds to M1. Is that clear? So this is same whether it is the lower branch as well as the upper branch. So this is what you need to remember. So we can write here P2 by P1 is P2 by P star at M2 and P star by P1 at M1. So then I can write here TT2 by TT1 is equal to TT2 by TT star at M2 into TT star by TT1 at M1. So similarly, I can write here PT2 by PT1 is equal to PT2 by PT star at M2 into PT star by PT1 at M1. So in similar way, we can find what is T2 if T1 is known, what is P2 if P1 is known, and what is TT2 and what is PT2 if the initial properties entering the combustor are known. And that is calculated from the Rayleigh theory. All these things, what you see here, these are all Rayleigh theory. Okay. Now, finally, this is the Rayleigh theory. Here is the charge that enters into the combustor. So here is the combustor. Now here is the injection of fuel that is injected into the combustor. So here enters at 1. So here it is P1, T1, TT1, PT1, let's say. So you have M1. Here it is M2. And then here it is P2, T2, PT2, TT2, and so on. Now here is the equivalent form either on the upper branch of the Rayleigh line going from 1 to 2, or it could be on the lower branch of the Rayleigh line if it's a scramjet engine going from 1 to 2. Now the same problem, irrespective of upper branch or lower branch, the energy equation is H1 plus half V1 square plus dQ is equal to H2 plus half V2 square. All this velocities here. So this could be HT1. This is HT2. So we can write here dQ is equal to HT2 minus HT1. So I can write here Q is equal to mass flow rate of the air that is entering into HT2 minus HT1. Or in other words, M dot O specific heat, the working fluid remains the same, Cp TT2 minus TT1. This is clear for all of you. this is dq, what we have seen before, to a section here where we are adding this heat here. So what is dq itself? This is the heat flux. So if you're considering the whole thing, this dq is nothing but the mass of fuel that is injected into the combustor. That fuel will have a calorific value QR. Sometimes it's also the heat of reaction, and some combustors, not all the fuel will be efficiently converted. There will be a combustor efficiency accounting for it. So this is what we see here. So we can write here m dot f QR, efficiency of the burner is m dot o Cp TT2 minus TT1. Now since m dot o and m dot f is given, we can also calculate the air fuel ratio or fuel air ratio depending on other parameters or no. This can be done through the Rayleigh theory. Okay, now I suggest maybe we'll take a short break and then we will start with the how long they want, because after that I'm going to work out the problems. It's in subsonic combustion and supersonic, so we'll work out these two problems and finish today's section right here. So we have learned the theory now we'll apply the theory after the break. So
when we were discussing the upper branch of the Rayleigh line on the HS diagram, we mentioned that at some specific interval, the change in kinetic energy will be higher than the rate at which the heat is being supplied.
I said if we want the flow to increase at a rate greater than the rate of heat addition.
So why is that the case? Why do we want it to increase that? What drives that particular?
Because it has reached a thermal choking point. An addition of heat will not cause the flow to cause any change. It will all go exactly the same rate. And the flow has not reached a choke condition. So at this point, at H max, we are adding heat. Any further addition of heat will not cause any change in the enthalpy.
Right. So how come we don't expect the horizontal line? Why does it have to drop down?
The flow requires some energy. The flow requires some energy because the addition of heat will cause nothing is going to change with H max. H max is reached the same. So the kinetic energy, addition of flow, addition of heat will cause the kinetic energy to go at the same rate. If I go like that, this will also go like that. If I want this to go a bit greater than the addition of heat, it doesn't have the energy. So it takes energy from the flow, and that's why we see that the red line is dropping. So from here, it is giving off this energy. It is giving off this energy, so it is losing its energy, but the flow is accelerating. And then the flow is accelerating and reaching the critical point, m equal to 1. That is how we see from this energy equation here. Otherwise, there is no way that if it is flat, you need the energy, additional energy for the flow to accelerate. That it receives from the flow itself, energy contained in the flow. Okay, so we will take problem number 1. Now it is your responsibility now to work out this based applying the theory, and we'll go step by step, and then we will see. So subsonic combustion problem. Problem number 1. It says a gaseous mixture of air and fuel enters the combustor, a combustion chamber with a velocity. So here it is 1. So this is 2. Enters in at the velocity v1 is equal to 60 meter per second at a temperature T1 is equal to 48 degrees centigrade and a pressure P1 of 0.345 bar. The heat of reaction of the mixture dq is equal to 1.163 megajoule per kg. Assume that friction is negligible and the cross-sectional area is constant, and the properties of gas mixtures are equivalent to air, which means R is equal to 287 joule per kg and gamma value is 1.4 and Cp is equal to gamma R by gamma minus 1 from the relationships between Cp by Cv and Cp minus Cv. Now we are asked to calculate the properties, calculate the static temperature T2. All of them are at the exit. So there are two parts. The part number 1 is to calculate the static temperature, static pressure P2, stagnation pressure PT2, stagnation temperature TT2, velocity V2 at the exit of the combustion chamber. Okay, so how will we proceed? It's important for us to know what will be the Mach number at inlet, what will be the Mach number at outlet. Okay, so the information what we have is, can we find M1? Yeah. So tell me what is T1 is equal to 48 plus 273. Convert that to Kelvin. Okay. And what is the M1? What is M1? So M1 is equal to B1 by C1. B1 is given in the problem as 60 meter per second. C1 is square root of gamma R T1. Gamma R T1. Gamma value is 1.4 for air, 287 joule per kg. Okay, we already calculated the temperature T1. We are solving problem number 1. Anybody got the value for M1? 0.167. So when you have the value for, so it's only for 2 decimal degree accuracy there. So we can say, shall we say M1 is equal to 0.17? Yeah. So if you can use the tables, so here you can see that this is M1 is 0.17. You can transfer this information into your paper. So which means that you have got the value for T by T star, P by P star, PT by PT star, TT by TT star. Okay, at M1 is equal to 0.17, you have T1 by T star. What's the value? 0.1538. P1 by P star, 2.3067, and then PT1 by PT star is equal to 1.2434, and then TT1 by TT star is equal to 0.1289. So now you have all these parameters at the moment here. Now how do we proceed? Now we have got some information from the Rayleigh table. What other information? So we have made use of this velocity, temperature. Now we have information on P1. Now we have information on the amount of heat, that is the energy content of the fuel. So we can write here from the energy balance equation, H1 plus half V1 square plus dQ is equal to H2 plus half V2 square. So we write here dQ is equal to HT2 minus HT1, or we can write here dQ is equal to m dot O into Cp Tt2 minus Tt1, and this is equal to m dot F, heat of reaction, into efficiency of the burner is equal to m dot O Cp Tt2 minus Tt1. This is a full equation, energy equation. Now in this problem we have no information of mass of air and mass of fuel, so we don't have to worry about this one here. We don't have any information on the adiabatic efficiency of the burner. So we have the energy content of the fuel is equal to Cp Tt2 minus Tt1. This is the information we have in the problem. Now this you can write here, QR is equal to Cp. I can take this Tt1 outside. Tt1 outside. What will be the form? Tt2 by Tt1 minus 1. This is clear. Now this is given in the problem. The energy content is given as 1.163 into, it's a megajoule, so into 10 power 6. So write this value here, 1.163 into 10 power 6 joule per kg K. What's the Cp value? Cp equal to gamma R by gamma minus 1. I don't know, so 1004 or 1005, what value are you getting? What value are you getting? 5? So Cp minus Cv equal to R, and then Cp by Cv equal to gamma. From this you can deduce this one. So this value is given as 1.4287. So whatever value you get there, substitute it. For sake of consistency of the class, shall we say this is the value you got? And then TT1. Do we know the value for TT1? This is T1, static temperature. We know the static temperature. Now there is a relationship between the stagnation temperature and the static temperature. This is the local temperature and this is the stagnation temperature. So the relationship between the local and stagnation is 1 plus gamma minus 1 by 2 m1 square. That's it. You remember this. Again, you get this from the energy equation. So what do you say here? So H naught is equal to, or total energy is equal to H plus half V square. So here it is Cp Tt equal to Cpt plus half V square. So from this you get this expression Tt by T is equal to 1 plus V square by 2 Cpt. So then if you substitute the values gamma r by gamma minus 1, then you will get Tt by T is equal to 1 plus gamma minus 1 by 2 m square. What is this value? T1 is known, 321. M1 you calculated 0.17. Gamma value is 1.4. So you can find the value for TT1. 332.8 K. $322.8 K. So now you can substitute this value here, 322.8 K, and then you end up with TT2 by TT1 minus 1. So what is the unknown here? TT2 by TT1 is the unknown here. Now calculate and tell me what is this value, TT2 by TT1. $4.586869. Is that what others are getting? TT2 by TT1. Okay. Should I slow down or shall we? It's okay, the face. Others are getting the value 4 point. Now we have to use this expression TT2 by TT1 is equal to TT2 by TT star corresponding to M2 from the Rayleigh table, and then into TT star by TT1 corresponding to Mach 1. What is M1? You calculated that value is 0.17. And this value is known. So this is known because you found out from the table. This is the only unknown. Find this value TT2 by TT star, find it, and then go to the tables to find what is the corresponding M2. Understood? So what is this value? What is TT2 by TT star? How much you said? 0 point? So what is the value? 4.587 into 0 point 0 point? Yeah, that is what you multiplied. What is this value? 0.59? 5912. This you have it in the inverted form. So you invert it and find this value TT2 by TT star. Yeah? Yeah. So take this value 0.5912 and find the value for M2. So the value for M2 is
0.40, in between.
yeah, so let's say 0.44. So once you know the value for M2, the value, then we can find out rest of the parameters. So now in the problem, we have found the value for M2. Then you can find the value for T2. T2 by T1 is equal to T2 by T star into T star, sorry, T star by T1. This is at M1, this is at M2. So M2 is 0.44 and this is 0.17. All the values are known. You can T1 value is given, so you can directly find T2. Tell me what is the value for T2. What's the value for T2? 1000. Is that what others are getting? Okay, then P2 by P1 is equal to P2 by P star. Sorry, not PT. P star by P1. One, two. What is the value you said? 0.282 bar. Anybody else got the value for P2? 281. Okay. What is the value for PT2? TT2. That is T2. TT2 you could have already calculated because you found the value for T2 by T1 already as 4.587. So what is the value? It should be in the order of 149 something. 148 80 80 or 82? 1480.6 Kelvin. Is there other? Oh, yeah, okay. What is PT2? So PT1 by P1 is equal to 1 plus gamma minus 1 by 2 M1 square power gamma by gamma minus 1. So that is the relationship between the local and stagnation. P2 is given already calculated 0.282. So PT1 by P1 is equal to 1 plus gamma minus 1 by 2 M1 square. From this you can find PT1, and then you can find this PT2 by PT1 is equal to PT2 by PT star and PT star by PT1. What is PT2? Point? Should be more than that one. 0.32. Yeah, 32, 2, 2, 2. So use this expression to find PT1. Anybody can tell me the value for PT1? 3522. And then use this expression to find PT2. 316. Yes. Yeah, 322 something. Yeah. Now, how do you find V2? In the table, if you look at this, there is no velocity expression. You can use the continuity equation as one of the ways to do it, or T2 you know, so that's one of the ways to do it. So rho 1 V1 is equal to rho 2 V2, which means V2 by V1 is equal to rho 1 by rho 2 is equal to rho 1 by rho star into rho star by row 2. Row 1 by row star at M1 can be obtained directly from the table, and row star by M2, row 2 can be obtained direct from the table at M2. So this is 0.17 and 0.44. What's the value you get here? 334. The range is okay. The range is, but accuracy is wrong. We need to check with one more. You used gamma t. You got the same value. You use this expression M2 is equal to V2 by C2. Okay. There can be some slight differences because we are approximating the value for M value. Because truncation errors will come. Okay, shall we move on to the next problem if you have worked out this one? Next part of the problem. Or you can try if people are trying. Let's finish this one here. So the alternate way I have also explained here, from the continuity equation you could also calculate V2 by V1. This is a bit more cumbersome because you don't know the value for, is the value for density given there? No. Then you have rho 1 is equal to P1 by RT1. You need to calculate it. Or you can, no, you don't need to do it. You can directly equate this V2 by V1 to this term. Is that clear? So V2 by V1 is equal to rho 1 by rho star into rho star by rho 2. 331. Which method? This method. The Mach number is equal to, yeah, okay. So something in that range, 331, 2, 3, 4, something. Okay, so let's move to the part B. The problem has two parts. So we have done the part 1. The part B of the problem says if the condition at the exit is choked, this is just an academic exercise. So what they're saying here is if the condition at 2 is critical value, M equal to 1, M2 is equal to 1. Calculate the stagnation condition corresponding to choking condition, which means stagnation means PT star, TT star, and the maximum heat that is applied to cause choking. So the maximum heat that is required to cause choking is Cp. In place of TT2, it will be TT star minus TT1. Understood, all of you? TT2 value will be TT star at M2 is equal to 1. That's the maximum one. So this is TT1. So to find this, Q max is equal to Cp TT1 and TT star by TT1 minus 1. So now you can see that this fits in directly at M1 is equal to 0.17. Directly from the tables you read that value here. And TT1 you already calculated. So you can calculate what is Q max. So this will be the maximum heat that will be required to cause the flow to choke. 2.19 megajoule per kg. Got the same value? Got it? So okay, once you have got it, from this value you can calculate what is TT star. That is what you're asked to find out. Calculate the stagnation conditions corresponding to choking conditions. So we are asked to find TT star and we are asked to find PT star. At M1, find TT1 by TT star and PT1 by PT star. We have already found out the value for PT1, TT1, so you can find out PT star by PT star and TT star. Anybody calculate the value for TT star or PT star?
250.
Okay, so TT star is 2501 K and PT star 28327 bar. What's the right value? 28 283. Okay, so you now understood the concept, how to use the Rayleigh table to calculate the combustion parameters. Now we'll finish this lecture with the last problem, supersonic combustion. So this will be the lower branch of the Rayleigh line. So here in problem number 2, air enters a combustor of constant area. Now here it is 1 and this is a 2. M1 is 3. Supersonic flow. So combustion is supersonic. The corresponding temperature T1 is 1500 K and the pressure P1 is 60 kilopascal. If hydrogen having a calorific value as 122 megajoule per kg is used as fuel, calculate the following temperature at the exit if the exit of the combustor if it is choked. I haven't made it explicit, but you can use the static temperature, okay? And the maximum heat flux, Qmax, fuel air ratio that is required to thermally choke the combustor exit, and what is the total pressure change across the combustor. So which means total pressure here is PT1, here it is PT star. So what is PT1 minus PT star by PT1 if you want to express it in percentage? So these are the parameters we are asked to calculate. So you can find out what is TT1 here from this relationship. TT1 by T1 is equal to 1 plus gamma minus 1 by 2 M1 square, and PT1 by P1 is equal to 1 plus gamma minus 1 by 2 M1 square power gamma by gamma minus 1. So you can use this expression to find PT1 or TT1 if required. Qmax is equal to Cp TT star minus TT1. At M1, if you can find TT1 by TT star and T1 by T star, then you can find this critical temperatures at the exit of the combustor. What is the value you get for the TT1? 4200 Kelvin. So from this you can find TT star, yeah? What is this value? 0.6654. And what is this value from the tables at M3? They're talking about TT star, yeah? What is 6422? TT star. What is this value? 0.2803. From this value, you can find out TT star. T1 already given us 1500. Divided by 0.2803. How much? 5,000 something? 5351. So what is Qmax? Somebody said 2 point. So Qmax is 2.23 megajoule per kg. TT1 already you have found out, which is there. TT star you have already calculated, and CP 1004.5, whatever the value you got. So you could also write here CP TT1 into TT star by TT1 minus 1. What is the pressure change in the combustor? See, at M1 of 3, at M1 you can find PT star by PT1 from the table directly. So 1 minus PT star by PT1 into 100 will give directly the percentage change in the pressure loss, pressure change in the combustor, total pressure change in the combustor. What is the value you're getting? Somebody said 20. That is what you get useful. What is the loss of it? 1 minus of that one. 70.798. All of you are able to understand? Yeah. So what is left out? What is the fuel air ratio required to thermally choke the combustor? So to calculate the heat flux, dq is equal to Cp Tt2 minus Tt1, but it is the heat that is required to choke the flow, Tt star by Tt1. This is the maximum. So what is the fuel air ratio that is required to choke? So which means we need to write the full equation. This is the amount of fuel that is required of that calorific value, which is 122 megajoule per kg because of the hydrogen. No efficiency information is given on the combustor, so we'll just assume that to be 100%, is equal to m dot o, mass of air, Cp Tt star minus Tt1. Now from this you can rearrange this equation. You can write here m dot f by m dot o, this terms here. Rearranging this equation, I'll get Cp Tt star minus Tt1 divided by heat of reaction, the calorific value of the fuel. Efficiency of the burner is not given 100%, we've taken it. So mass of fuel to mass of air is the fuel air ratio that is required to thermally choke the combustor. How much he said? 0.018. Okay, all of you have finished this one? So you got the grasp about what we did today. Yeah. So this morning we went through the overview of the gas turbine powered engines. We looked at the turbojet engine. We looked at the turbojet with an afterburner, and we looked at their corresponding cycle diagrams. Afterburner is used for thrust augmentation. You use it only when it is required because it also related with the penalty of fuel consumption. For commercial applications, fuel consumption is of importance, so we have to recover the waste, is to incorporate a power turbine, run a fan, and that could be done in two modes: either bypass it and expand it in the nozzle, or bypass it and then finally mix it and then expand it. So that is unmixed exhaust turbofan and mixed exhaust turbofan. And then we looked at the turboprop, turbo shaft. And then we briefly looked at the ramjet, and scramjet has no moving parts. And in the afternoon class we looked at the combustion process through the Rayleigh theory, where we are able to demonstrate that we can use the Rayleigh theory and use the Rayleigh tables to calculate the combustion parameters. So you can calculate the fuel air ratio, you can calculate what's the pressure, temperature, what's the Mach number, how all these things changes in either it's a subsonic ramjet or it's a supersonic combustor. So I think with this we will finish today's lecture, and tomorrow we will start morning at 9:30. 9:30 we will start with the introduction to shocks. Yeah, and bring the calculator, because we will be trying, we'll also try to solve problems side by side. We'll try to solve, I think there are more number of problems tomorrow, I think. Yeah. Okay, so we'll bring a calculator and we'll try and work out majority of the problem sheet as much as possible. Okay, so I think that's it. If you want to make any announcements, you can. Thank you very much for today. Yeah.
Tomorrow also we have a lot of day after tomorrow onwards.